Все равно не слышно. А вот трансляция уже запустилась, похоже.
Хорошо. Then I'll switch to English. And so today I'll continue the topic of the last discussion, which was conformal blocks. And the last time I didn't get to talk about the main thing I didn't get to talk about was the Zamolodchikov-like recursion relations for conformal blocks. And so that's going to be the topic of today. And so these recursion relations were introduced for various other conformal blocks by Zamolodchikov in '87, if I remember correctly. But recently, the analogs of these recursion relations, which use the same idea, are also kind of introduced into the world of higher dimensional global conformal blocks. And the first work which I think used them was this paper by Klaus Polland and Simon Staff in 2013. And then, since as we discussed last time, there is a fair amount of different kind of conformal blocks in the sense that there are different spins for external operators and so on. People have used them somewhat for some work. So the scalar conformal blocks is what was used in this paper. And that's been the standard tool to compute the scale conformal blocks since then. So everybody who does numerical conformal bootstrap computes their conformal blocks using these recursion relations. But for other conformal blocks for spinning operators, there has been less. They have been less popular, in part because of, I'll explain why. But the main paper which discusses the recursion relations in kind of more general higher dimensional context outside of the world of scalar blocks is this paper by I think Donis Rezani and Yamazaki in 2015. And so basically today I'll kind of review this recursion relations, and then they'll discuss our recent paper from last year where we kind of computed the ingredients of this recursion relations for all blocks in 3 dimensions. And that's something that I think is useful for numerical bootstrap in 3D. So let me start. First, let me just briefly address the question of what kind of conformal representations we have in higher dimensional CFDs. And let's start with Hilbert space of our conformal field theory. And just to avoid some confusion that some people apparently have, is that when we work with quantum field theories, with general quantum field theories, we often talk about, in Minkowski space, we often talk about quantization by flat slices. So we have some flat slices at constant time, and we associate Hilbert space with this constant time slice. And alternatively, in CFTs, including signature, people often talk about radial quantization, where the Hilbert space is associated to a sphere. And so the important point that I want to stress is that this is the same Hilbert space here and here. What the difference between these two pictures is simply in the conformal transformation, which maps here to a plane, and also that the Hamiltonian in these two pictures is different. Here, the Hamiltonian is a dilatation. So in the radial quantization, Hamiltonian is a dilatation operator. Here it's a translation. If you map one to the other, then the translation in time will not map to dilatations. So, but nevertheless, the Hilbert space is the same. It's just that the Hamiltonian and kind of the picture in which you look at it is slightly different. And now, so this Hilbert space that we have, it's supposed to be, of course, as usual, interrepresentation of the symmetry group. And the symmetry group that's interrepresented, as discussed last time, is the Lorentzian conformal group SO2, SOD, and you also have to take its universal covering group, because SOD, it's not simply connected. It has its maximal compact subgroup contains a SO2 factor, so it contains like the fundamental group of SOD, without taking universal cover is Z, and so when you take the universal cover, you get a much larger group, and that's so it's an infinite sheeted covering of the SOD, 2. But that's a technical point, it's not so important. So that's one point. Sorry. That we have a unitary representation of SOD, 2. Another point is that, as usual in quantum field theory, we have the imposed constraint that the spectrum of the Hamiltonian in this picture is positive. So the energies in quantum field theory are non-negative, and so we want the spectrum of H to be a part of the positive real line. Now, this condition is important because, well, it's obviously physically important, but from our discussion, it's important because Hamiltonian is, of course, is a generator of this group, and therefore the question of whether its spectrum is positive or not is a question about the representation theory of this group. So when we say that, usually we would say that Hilbert space decomposes into direct sum of unitary irreducible representations of this group. In this case, we actually say more. We say that the Hilbert space decomposes into unitary positive energy representations of conformal group. And these representations, you can go ahead and classify them. And the way you do this, you kind of look at the dilatation operator. You say that the dilatation operator essentially has to have positive eigenvalues because the energies are positive. There is an argument for that. And then you say that, okay, if the dilatation eigenvalues are positive, then there must be states which are not by special conformal transformations, blah, blah, blah. And you arrive to this picture where you can describe the states in irreducible representations with these properties as kind of, they can be described as if they were created by a local operator acting on vacuum and radial quantization, and then its descendants. And the statement, so this so far is just like a representation theory statement that we asked what are the kind of representations which are unitary in positive energy, and they can be constructed in this way. And the operator state correspondence tells us basically that they are not just constructed in this way formally, they are actually constructed in this way physically, in the sense that inside of the Hilbert space H, these representations are indeed generated by taking local operators and acting on the vacuum state. And so these representations that kind of are more or less familiar, I guess, for everyone who studied 2D CFTs. It's just that in 2D CFTs would have more kind of lowering operators. Instead of just P, we would have like L -1, L -2, and so on. But here in higher dimensions, we just only have P, and the representations with this structure, sometimes called generalized Fermat modules, for the conformal group, and the requirement that they're unitary is manifested in some constraints on the highest weight. So let me discuss this construction of these representations a bit more formally. So, as I said, the representation, the reducible representation associated to some primary operator O is kind of spanned by these states, which are O acting in a vacuum and radial quantization, P times O acting in a vacuum, 2Ps, and so on. And if we look at the kind of lowest dimensional state here, this one, then we can see that this state is an irreducible representation of these states labeled by different spin indices on the operator O are in form an irreducible representation of the algebra generated by dilatations, rotations, and special conformal transformations. So the dilatations act on the states simply by by delta, which is the scaling dimension of O. The rotation generators act by matrices of some irreducible representation of SOD rho, and special conformal generators just act by 0. And if you want to talk to mathematicians, so then the way you describe this subalgebra is that it is some parabolic subalgebra of conformal, of Euclidean conformal algebra P, And the states here, they form some reducible representation L of this parabolic subalgebra. And then all the other states are just P acting on the states in this highest weight. And the way we would compute, say, the action, let's say we want to take a state, this one, and act on it with, let's say, K. So we would write K on the left, and we would commute it to the right using the commutation relations until it hits O, in which case it gives 0. And the kind of formal way of saying this is that we can construct this representation by taking the universal enveloping algebra of G, which is where G is the conformal algebra, and tensoring it with this highest weight representation L, and allowing the generators of the parabolic algebra P to go through this tensor product. So that's kind of just from description. We won't actually need it, but that's how we construct what's called the generalized, sometimes called the parabolic Fermat modules. The usual kind of, I think what is called just the Fermat module would be if this would be if our highest weight state didn't have an index. So we had a unique highest weight state, and so when we would, instead of parabolic algebra, we would use it's called Borel subalgebra, and the L would be one-dimensional. So this is the case in, say, on the study representation theory of Versor algebra, because there we just have some state H, which is just one state, and it's annihilated by all Ln with n greater or equal to 0, greater than 0, and this L0 and Ln with positive n's form a Borel subalgebra, and this is just a Fermat module. Here it's more complicated because for Lorentz group, we include both the we don't just say that the state is annihilated by all the raising operators of the Lorentz group. We are kind of forming a representation. In any case, it's not super important. I think it's probably everybody understands how these representations look like, and just the main point I want to convey is that technically these are generalized Fermat modules, and if you want to study theories and some properties of this representations, then this is the theory of generalized Fermat modules. Now, the important point is that if we remember that in radial quantization, Hermitian conjugation of P is K, then we can compute inner products between such states. So in the usual way, so if we want to compute inner product with this guy with something else, we take its Hermitian conjugate, so this gets replaced by K, and it's the usual kind of computation. And the statement is that as long as, so the unitarity of these representations is the condition that the norms that we compute in this way for any state and the representations are positive. And in the in higher dimensions, there are no conditions on central charge, because central charge doesn't enter into the conformal algebra in any way. And the conditions are in general just the statement that the scaling dimension should be both greater than some positive number, which is determined by the Lorentz representation. So for example, for traceless symmetric representations, we have delta greater or equal than traceless symmetric spin plus spacetime dimension -2. And for scalars, we have delta greater or equal to d - 2/2. There is an exception that for scalars, delta can be equal to 0. So yes, so these are our representations, and it's this inner product is going to be important for us. So let me introduce a notation for it. So first of all, we can denote by H0, H1, H2, and so on, the spaces of states at different levels of the representation. And in each at each level, we can choose some basis states 0i, 1i, 2i. I'll denote them in this way, where the index I just goes over some set. So for example, if we take phi to be, sorry, operator O to be just a scalar, then there is a single state in the level 0 subspace, and I just take single value. In level 2 subspace, we'll have, sorry, in level 1 subspace, we just have states labeled by mu. So in this case, I is essentially going to be mu, and so on. And then since this operator states in different subspaces have different scaling dimensions, the states in H0 are orthogonal to states in H1, they're orthogonal to states in H2, and so on. So this matrix of inner products, the inner product that we can define for the representation is kind of block diagonal inside of that kind of, it's only non-zero within H0, non-zero in H1 and H2, but between each other, these spaces are orthogonal. So we can completely describe it by this matrix is Qnij, which is just the matrix of inner products for states at level n. And you can go ahead and compute these matrices, and if you do the calculation, you'll find that at each level, these matrices will be some polynomials in delta. So for example, in this case of phi, when local operator O is some scalar phi, for example, if we want to compute the matrix for level 1, then what it is it's given by this expression. So we take conjugate to p phi, and we take then p phi without taking the conjugate, and we take the commutator, so this becomes linear plus commutator kp, and this is just 2d delta mu plus minus 2m mu. So since phi is a scalar, then m mu gives 0, and 2d delta mu gives this 2 delta delta mu. And you can do the same calculation at higher levels, and you get some polynomials in delta. And this unitarity bound here is, of course, just a statement that provided that delta is above a certain threshold, all these matrices are positive semi-definite. So for example, simple exercise, if you take and check that this matrix is positive semi-definite, you'll find this unitarity condition on scalars. So I guess this was some really quick, but also probably a bit incoherent review of these representations from the point of view that you require. I'll move now I'll start moving towards conformal blocks now. So before I do that, are any questions about this part?
You say that these are polynomials in delta, but do they depend on some other quantum numbers?
So the only quantum numbers that there are is delta and the Lorentz representation of
so of this J, yeah, this spin J or whatever.
Yeah. So they, of course, would depend. Oh, so this example here is for J equals 0, so for scalar operator for O equals 5.
I see, because it's, yeah, otherwise it's strange. Yeah.
Yeah, if it wasn't scalar, then of course this matrices would simply have more indices, because you would have so these indices only account for the indices of the momentum generators, right? If phi was a vector, then there would be an extra index in this matrix is coming from the vector index of O. And the matrices would, of course, have a different form. But at fixed Lorentz representation, it's just a polynomial in delta. Okay, so let's move on. Now, let me remind you that the 3-point functions in higher dimensions are not completely fixed by conformal symmetry. They're fixed by conformal symmetry up to some number of 3-point coefficients, 3-point couplings, which are labeled by lambda alpha, and any 3-point function, any physical 3-point function can be expanded in basis of some standard 3-point functions, which are called tensor structures. And I'll just denote them in this way. So I'll denote them in the same way as physical 3-point functions, and just I'll put an index alpha under them, which means that this is a basis element with index alpha for the space of conformal invariant 3-point structures. And I'm free to choose whatever basis I want, as long as it's complete, of course. And if somebody, so if you take some concrete 3-point tensor structure, so we take this expression, we have 3 operators, so 1, O2, O, they have some variance, and this is A, B, C. So this is, and we take some concrete label alpha, so this is some concrete function of x1, x2, and x. So for example, if we were working with scalars, right, I would say that phi1 of x1, phi2 of x2, phi of x, and in this case there's a unique structure, so it put index 1. Then this would be, just by definition, this would be some product x1 minus x2 to like delta 1 plus delta 2 minus delta, and then 3 other terms in the denominator. So this notation here is just a concrete function of x1, x2, and x. And if we know this function, this allows us to compute kind of this inner products between the state created by O1 and O2 and these basis states that we introduced just in the previous slide, assuming that this is the kind of the physical value of the 3-point function. And the way we do this is, for example, if for example, if we take level 0, then our index I is just the Lorentz index of the operator, and this basis states are OA of 0 acting in the vacuum, right? And so if we insert this here, then this just tells us that, okay, to compute this inner product, what we need is we need to take this function and just plug in x equals 0. Now, if we go to level 1, then we'll have that our indices are now mu and A, and we have here P mu. But P mu acting on O just gives a derivative. And so again, plugging this in here, this tells us that, well, to compute the inner product at level 1, we need to take this function, take derivatives with respect to x, and then set x equal to 0, and so on for all higher levels. So this is just to explain what this notation means. And then if you go back to the definition of conformal block, and then the conformal blocks will be computed by just taking the state created by O1 and O2, the state created by O3 and O4, and assuming some particular 3-point tensor structures for the way they create states, and just summing over all intermediate states in our representation of HO. But since this basis of states that we chose, and I is not necessarily orthonormal, I mean, by looking at this in matrices, you can definitely see that it's not orthonormal. So to account for this, we need to sum over different i's and j's and insert this inverse of this matrix Q here. And this expression will give us the conformal block after we factor out the 4-point tensor structure. And from this expression, you can see that since Q was some polynomial delta, in general, the inverse to Q might have poles. For example, in this case with scalars at level 1, matrix Q is just diagonal and has overall factor delta. So if you take Q inverse, then we obviously have factor 1 over delta coming from here at level n equals 1. And so we see therefore that conformal blocks will have general poles, and these poles are associated to matrices Qn becoming degenerate. And the idea of the recursion relations is, of course, to study these poles and understand their residues. So Zamolodchikov first realized this is useful for Versor conformal blocks, and here I'll just be discussing the higher dimensional conformal blocks. So as I said, we get poles when some of the matrices Qn cannot be inverted. And if a matrix cannot be inverted, it means that, well, if the symmetric matrix cannot be inverted, it means that it just has some null vectors. It has some vectors V, has at least one vector Vj, which it annihilates. And in terms of our representation, what this means is that if we take this component Vj, which we construct by finding the null vectors of this matrix Qij, then and construct a state psi using this coefficients Vj and our basis states, then this state psi is going to be null in the sense that it's orthogonal to any other state. And the reason for that is that it's orthogonal to any other state at any level other than n, just because the eigenvalues of the rotation operators are different. But it's also orthogonal to all the states at level n because of this condition on Vj. And so we find the state psi prime such that it's orthogonal to any other state. So we find the state psi which is orthogonal to any other state psi prime in our representation. And an important point is that such states psi, they form a representation themselves. So they form a submodule of our Verma module. And the way to see this is that if we know that for any psi prime, psi is orthogonal to it, then if you take some conformal generator G and act on psi and take inner product with some psi 2 primes, we can interpret G as acting on psi 2 primes, and this is just some psi prime, and since our psi is orthogonal to all states, it's also going to be, I think it's kind of straightforward. So it's clear that G psi is also going to be orthogonal to everything. It's basically the statement that the inner product is in invariant form. So yes, so the statement is that as long as we have pole, like whenever we have pole, we have null states, and these null states form a submodule. So what this means is that having a non-trivial submodule, so this submodule is proper because the highest weight state is obviously not null. The states at level 0 never have vanishing norm because there is no computation to do. It's just the conventional have norm 1 essentially. And so null states do not span the full HO. And so it means that HO has a proper submodule. And so it means that HO is not a simple module. So in other words, it's not an irreducible representation. So in other words, the poles can only appear in conformal blocks when the representation HO becomes reducible. And when we have some representation, well, so the claim for generic delta for most values of scaling dimension, this representation HO will be irreducible. And only for special values of delta, it's going to stop being irreducible. And the question is, what precisely happens? How precisely not reducible it becomes? And it turns out that it's very different. The picture is very different for even dimensions and for odd dimensions. Or maybe I should say that once you have written all the final formulas, you can analytically continue in scaling dimensions. So odd-dimensional case is the case of is really the case of D any complex values except even integers. If you analytically continue after, I don't want to discuss what it means like to have a conformal algebra in fractional numbers of dimensions, but once you get to the final formulas, once you get to the final conformal blocks, you can analytically continue in D, and the odd dimensional case corresponds to generic values of D, and it's the even dimensional values which are special. And the case of odd dimensions or generic complex dimensions, we understand enough for us to be able to compute conformal blocks using it. And
sorry, I'm gonna ask a question.
yeah.
So do you remember correctly that there are general formulas for conformal blocks in even dimensions?
Yes, there are closed form formulas in terms of 2f1s for conformal blocks in even dimensions. That's true. But
how is it combined with the fact that in this case looks more complicated? As you're right.
Right. So what I'll so what we'll discuss now is that in general dimensions, in all dimensions other than even dimensions, the conformal blocks have simple poles in delta, and this residues of these poles are other conformal blocks. Now, in even dimensions, what happens is that you start having higher order poles. And so, for example, if you can take explicit formulas for scalar blocks, let's say in 4D, and you can look at this formula. It will be products of some 2f1s. You can check when these 2f1s have poles, and you'll find that even 4-dimensional scalar conformal blocks have double poles. And so the coefficient of the leading singularity of the second order pole is again the conformal block, but the residue, the coefficient of like 1 over delta minus delta naught, that coefficient is not actually conformal, it's something else. And you can actually, well, what we can do is we can take the formulas for these recursion relations in generic D, and we can carefully take the limit of D going to even dimensions, the scalar blocks, let's say, and we can find the recursion relation in 4D if you want. We have done this, we use this for computing 4D scalar blocks. And this gives the same results as the 2f1s, but what we don't understand is how to compute these recursion relations kind of from first principles. Just start in 4D directly and compute the recursion relation, understand what is the residue, what is the coefficient of leading order singularity, what's the coefficient of subleading singularity at the pole, and kind of write down the recursion relation directly in 4D without kind of any tricks. That's just not understood. I'm not saying also, I'm not saying that it's necessarily hard to understand, it's just that it's not in the literature, and I think it's an interesting problem to do, to understand it.
Okay.
But yeah, so as I was saying, we understand the kind of the representation theory enough for computing conformal blocks in in odd dimensions. In even dimensions, we don't really understand it. At this point in published literature, it's not explained how to compute even dimensional conformal blocks kind of from first principles in the same way as I'll explain 4 dimensions. And when I say we, by this I mean kind of the people who work on numerical bootstrap, and mathematicians, of course, understand a lot about the way these representations degenerate, and there is an interesting story that I won't have time to get into, unfortunately, but and I think this can be solved. It's just that it hasn't been solved as of now because people have been using different techniques, I guess, and hasn't attracted so much attention. So I'll focus on odd dimensions mostly. the rest of the talk. So in odd dimensions, the picture is very simple of what's happening to this representation is that we have our representation HO, and then we find that when conformal blocks have a pole, the poles happen when there is an non-trivial submodule, and vice versa. When there is a non-trivial submodule, we can show that the pole must appear. And the non-trivial submodule that we find inside of HO turns out to be itself a simple submodule. So it's a very simple kind of picture when HO used to be simple, and then it just developed a single irreducible submodule at a special point. And this irreducible submodule M is generated itself by a highest weight state. So it kind of is similar to parabolic module itself. So the statement is that there is some set of states psi A inside of HO, and the states psi A form an irreducible representation of this algebra generated by dilatations, rotations, and special conformal transformations. It's just that now they have different quantum numbers compared to the highest weight states of HO. So dilatation acts by delta plus n, where n is the level at which this psi n A sits. They transform in some new irreducible representation of Lorentz group rho prime, which is in general different from the Lorentz representation that generated HO. And K mu still act by 0. So this is what we would call a primary descendant, because it gets annihilated by K mu, and the reason it's annihilated by K mu is that we have tuned delta to be some very special value such that this happens. And this state, it generates the entire submodule M. So M is just the span of psi A and all the P generators acting on psi A. So for example, if we recall our example, if you consider this case when the operator OA that generates HO is just the scalar, fine. We can recall that, for example, the first level matrix of product was proportional to delta. So if we set delta equals 0, we find null states already at level 0, sorry, at level 1. And indeed, in this case, you can check that this state psi mu, which generates all other null vectors, is just given by p mu acting on phi. And so like it's already at first level, all the descendants are inside of M. But an important point is that even though that this structure kind of looks like M is itself a Fermat module, it's not a Fermat module. And the reason for that, you can see in this example that if you consider this combination in a Fermat module would be some non-trivial state. However, inside of M, this is 0, because obviously if you plug in what psi is and symmetrization, it will give you 0. So the correct statement is generically this M is a quotient of a generalized Fermat module by its null states. So if you look at psi M here, you get a vector set of states because they have label mu. We set delta equals 0 and psi mu live at level 1, so delta equals 1. So you get that psi mu is a vector of delta equals 1. And you can build a Fermat module of starting from such a highest weight, and you will find that this state is not 0 inside of this Fermat module, but it's null. And the way you get M is you quotient this Fermat module by all null states. So in general, not dimensions, this submodule that develops inside of our representation has a structure that it's a quotient of a Fermat module by null states. And if we now go back to our formula for conformal block, which involves the sum over levels and over I and j, I get j here, and sum over I and j with this Q inverse, then after a bit of staring at this formula, you can convince yourself that this suggests at least that the residue is related to the Verma module, sorry, that the residue is related to the conformal block for this psi. And to actually show that this is the case is a bit heavy on notation, so I'm not doing this very explicitly, but what you can do is you can look at this matrices of inner products Q, which depend on delta and rho, where delta is the scheme dimension, rho is the Lorentz representation of our operator O. And you can restrict this matrices to this submodule M, and if we take delta to the special value delta star at which M appears, then kind of since M consists of null vectors, this Q restricted to M just becomes 0. And so what you can do is you can divide it by delta minus delta star to get something that's non-zero, and you can prove that as you take the limit, in the result you get just the this Q matrices for this Verma module that M is a quotient of. So it will have the level bit shifted, and it will have quantum numbers which correspond to psi. So it will have delta star plus n, and it will have this rho prime, where delta plus n, delta star plus n, and rho prime are the quantum numbers of this psi which generates this module. And so you can see that kind of the part of the residue which comes from Qn inverse is already Q for some other quantum numbers, and similarly here for this inner product on the left and on the right, what you need to observe is that so this highest weight null state that we have that generates M can be always expressed as some bunch of P's acting on O in some particular linear combination. And if you can commute P's to the right, you'll find that they turn into derivatives. And so, and if you interpret everything correctly, then you can check that the way you can express the state is some differential operator DAB acting in OB and related at 0. And this differential operator is conformally invariant. And if you take this differential operator, so if you remember that this inner products, they are constructed from this 3-point tensor structures. And if you take this 3-point tensor structure and you plug in this differential operator inside of it, you'll find that you get something which again transforms like a 3-point function, because this operator is conformally invariant, but now there's new quantum numbers. Maybe I should have denoted this by psi. So, and because it transforms like conformally invariant 3-point function with some new quantum numbers, you can expand it in the basis of tensor structures for these quantum numbers, and you'll get some expansion coefficients. And again, staring at this expression for the conformal block, you find that you find that there is a subset of states which lead to false in this Q inverse, and the residues which come, the part of the residue which comes from Q inverse is just again Q inverse, but for some other Verma module, and the states that contribute to the residue themselves can be written as derivatives of, well, the states here can be written as P acting on this psi, psi itself is can be interpreted as a derivative of O, and the tensor structures with derivatives of O expand in terms of other tensor structures. And if you stare at it for a while, you can convince yourself that what happens is that the residue of the conformal block is going to be another conformal block, and but it will now have different 3-point structure labels, and it will be multiplied by this L and R matrices, where L is this matrix which expands, which solves this equation, and here it's sum over alpha prime is understood, and R is the same but for O3 and O4. And so that's the kind of the key statement for the recursion relation, that the residue of a conformal block is another conformal block, and the coefficient is by two matrices acting on the 3-point tensor structure indices of the conformal block. Now, I realize that it's a bit like I described in a very confused way, but I also couldn't come up with a way which would not involve like tons of heavy notation and be even worse. So maybe if people did not understand something of this, it would be a good point to ask questions and discuss this, and then we'll move on to using this.
Probably I missed what alpha and beta stands for.
So alpha and beta in conformal block, they stand for 3-point tensor structure indices. So you can think of, as we discussed last time, of a conformal block as kind of gluing of two 3-point structures, and alpha and beta just label these 3-point structures. Because so the way you use this 3-point structures in 3-point structure indices is that if you want to compute the 4-point function, so what you do is you sum over kind of O, and you sum over alpha and beta, and then you have the 3-point couplings which have some labels alpha, and you multiply by conformal block with this alpha beta labels. These labels are needed because the 3-point function is not uniquely determined by one number. Instead, it's several numbers, and the several numbers are labeled by alpha and beta for each of the 3-point functions.
So this is 3-point structure constants, yes?
Yes. Alpha and beta label different 3-point structure constants for a given 3-point function.
So this is like each alpha and beta is like collection of three primary three labels of primary fields in this theory, yes?
No. So let me maybe remind about this. If you choose, so let me go to this equation here. If you take some particular 3-point function, say O1, O2, and O, some particular O1, fixed O2, and fixed O, right? Then this is a physical 3-point function, and it's supposed to be conformally invariant. It's supposed to satisfy ordered identities. And you can ask, okay, what are the conformal invariance conditions? What are the constraints that they imply for this 3-point function? And you solve these constraints, and you find that there are finitely many 3-point functions that solve the conformal invariance constraints. And you choose some basis of solutions, and you label this basis of solutions by some index alpha. And the physical 3-point function should be expandable in this basis because it itself is conformally invariant. So for example, if the operators O1, O2, and O are scalars, then there's only one conformally invariant 3-point function, and it has this kind of form. So there's only one value for index alpha, and there's just one 3-point coupling for the given triple of operators. However, if you add spin to O1, O2, and O, then there can be more. And in that case, you need to specify more labels lambda. multi-point couplings lambda, and so alpha will go maybe like over 2 indices or 3 indices or 25 indices, depending on what the spins of these operators are.
Okay, probably understood. And in recursion formula, you got the same indices on the left and on the right side. Yes.
No, so maybe I should write it
They're different.
explicitly.
Okay.
There's sum over alpha and beta, and so the way you can think about this is that there is this the way you can describe this is, suppose that the kind of suppose that this suppose that the physical 3-point function, imagine that the physical 3-point function of a 1, O2, and O is just equal to one basis 3-point function. It just, for the sake of the argument, suppose that it's equal to the basis 3-point function. And what happens is that now, assuming this, you can ask what is the O1, O2 psi 3-point function, where psi is this null descendant. It's the primary descendant of O, right? And it again should be expressible in terms of you should be able to write this as some sum of some lambda coefficients times some 3-point structures, right? And what this L alpha prime do is that they're exactly these coefficients. So these are the same things as it says here, because psi is this expression, it's d acting on O. And what we're doing is we're taking this 3-point structure, we are applying this differential operator, and we're getting some new conformal invariant 3-point function with these new quantum numbers, these are the quantum numbers of psi. And so it should be expandable. I should probably have written some here explicitly as well, in terms of basis 3-point structures for alpha prime, sorry, for psi, which are labeled by alpha prime, and the coefficients. And the conformal block has alpha and beta here, and alpha prime, beta prime here, and they're transformed into each other by this L and R, where L is defined this way, and R is defined in the same way, but for O3 and O4.
And L is not differential operator, it's just a number, yes?
Yeah, L is just a bunch of numbers, precisely. Differential operator is only here. So one example of this differential operator was here. So in this case, the differential operator would be d mu phi. When O is scalar, is dimension 0, then the d is just d mu. Okay. So let's move on. So if we go to this expression here, I have written here explicitly the indices of these operators A, B, C, D, and everything depends explicitly on x1, x4, and the same on the left-hand side. And these conformal blocks, as we discussed last time, you can expand them in terms of basis 4-point tensor structures, and then they become functions of cross ratios. And so if you do this, this is the same for both sides, and then you get this functions where instead of ABCD labels, you now have the label I for 4-point tensor structures, which is the same on both sides, because here nothing happened to this indices A, B, C, D. It's the same indices. Nothing happened to the coordinates, the same coordinates. And you just now have a function of cross ratios z and z bar, and it's the same z and z bar on both sides. So for example, if we reduce to scalar case, then there is no index I, there is no index alpha beta, they're just trivial, they take on the one value. And so this matrices, both of them just become numbers, and so you can just know their product by R. And we get this simple statement that the scalar conformal blocks, which depend on delta and trace symmetric spin J, have poles, simple poles, and the residues are some coefficient R times conformal block at new scalar dimension delta star plus n and some new spin j prime. And so to understand this residues, the two things that we would need to do is to compute this, to understand this values of delta star. When some null disappear, we need to understand which level they appear. We need to understand the representation rho prime. So in this case, it's j prime, which they transform. And then we would need to compute this matrices L and R. And if we do this, we understand the poles of conformal blocks. So in case of scalar blocks, people have done this in this paper. And well, what they've done actually is they did not go through this procedure that I described. What they did is they computed the conformal blocks order by order in some series expansion using Casimir equation, and then just stared at these expansions and guessed, looked in these expansions, they could see the poles explicitly and the residues explicitly, and they just guessed these formulas. And then they were later rederived using this method, this construction that I just described. But I just wanted to go through this example just to show you that it's all very explicit and to explain how it's used in practice. So we have this statement that the conformal blocks have poles at some locations delta I. The residues again conformal blocks is delta I plus ni, some new spins ji, and there are some residue coefficients ri that needs to be determined. And it turns out that there are three families of poles. They have various, so they within each family, the poles are labeled by integer k, which goes from 1 to infinity in two families, and it goes from 1 to j in the third family. These coefficients ni, they are just k or 2k, and this is kind of the k and i's are the order of differential operator d that we discussed, and so it's just k in two cases and 2k in another. Some explicit values for j I, which appears on the right hand side. Then there's explicit values for the delta I at which the poles appear. And so this, you can see that this is written in generic dimension d. And what you can check from this table is that if you are in odd dimensions or in any fractional dimensions, then these delta i's never coincide. So these delta i's for different families, they're always in different places. However, what happens when you go to even dimensions is that this family, which contains d over 2 in this delta i's, now this d over 2 becomes an integer and it can collide with other families. And it indeed happens, and this leads to double poles and it complicates the recursion relation. But in any case, there is a classification of these poles for scalar conformal blocks, and you can the explicit residue matrices are known. And the way it's used is as follows. You first observe that at large delta, the conformal blocks have this behavior. They have a factor r to the delta, and then some constant, delta independent constant, where r is defined through rho and rho bar, and rho and rho bar is just some function, so it's in the bar. And the way you see that this is true is you just solve Casimir equation at leading order in delta, Casimir differential equation that we discussed last time. And then from this same equation, you also get an explicit form for this function h infinity. And so what you do with the knowledge of this asymptotic behavior of conformal block, what you do is you define a function h delta j, which is just cutting out this r to the delta singularity from the conformal block. So for conformal block, we knew that the residues had this form. Just plugging in the definition of h, we find that it also has the residues, poles and residues, where residues are again proportional to h. It's just that now we have an extra r to the power ni here. And if these conformal blocks had essential singularity delta equals infinity, now these guys just tend to a finite limit. And so since we now have a function for which we know all the poles, h, for function h, we know all the poles, we know all the residues, and we know that it tends to constant infinity. We can conclude that this function actually can be written as the sum of the term at infinity, of the value at infinity, plus the sum of all the poles times the residues. And this expansion, so this is what we call the recursion relation, because it expresses function h, again in terms of function of known function h infinity, and again in terms of function h. And what we do is we use this expression to construct a power series expansion for h in powers of r. And the way it works is that here in the sum, all ni's are necessarily positive integers. So if you want to consider to find the leading term in r, so r to the 0 of h delta j, what you do is you just drop this entire sum, and you just take the r to the 0 term from this expansion, from this function, which is known. And if you want now to compute, say, r to the first term, you only keep the terms in the sum, which there are finite and many, which have ni equal to 1, and you use the kind of leading order result that you have for h in these terms, and you expand this function to two more orders. And you can repeat this recursively, and you find the power series expansion for h of z and z bar in powers of r, and the coefficients in this expansion are function of the kind of the ratio between rho and rho bar. So if you remember from here, the r is kind of the product of rho times r bar, and in this expansion here, you'll find the coefficients of the functions of the ratio for rho bar. And if you expand them, they turn out to be polynomials in this ratio, and so you'll get an expansion in terms of powers of rho and rho bar. And this expansion will converge when both rho and rho bar are inside the unit disk. In terms of z and z bar cross ratios, rho and rho bar being inside the unit disk corresponds to z and z bar being anywhere in the complex plane away from these two cuts, away from the cut from minus infinity to 0 and from 1 to plus infinity. In numerical bootstrap, one wants to compute the conformal blocks around the crossing symmetric point, which is z equals 1/2. And in terms of rho and rho bar, this crossing symmetric point gets mapped to 0.17. And so this expansions converge pretty quickly for this purpose. And also I should note that this blue region, the unit disk of rho and rho bar, is also the same region where the entire conformal block expansion of the 4-point function converges. So in this sense, this is kind of the best you could hope for in some sense. Of course, you can analytically continue conformal blocks to wider region, but the conformal block expansion converges on this unit disk. So knowing the conformal blocks there is already quite good. Okay, so are there any questions about this? Because now I'll just move on to the case of general 3D blocks and go over that in the remaining. Do I have like 15 maybe more minutes?
Yes, of course.
Okay. But okay.
So I wanted to ask you, is there any explicit formulas for this H infinity?
Yes. It is said the way you get it is that you just solve the quadratic conformal Casimir differential equation at leading order in R, and the explicit expression for it is something like I don't remember it exactly, but I probably should have written it down. It's something like 1 over square root of 1 minus r squared. Then there is some Guggen-Bauer polynomial j d minus 2 over 2 of rho plus rho bar over r, to R. It's some very explicit expression, and it's like this is not exactly it, but the true expression is not more complicated than this, than what I've written here. Okay. Right. So now we'll discuss. Yeah. So let me maybe give a bit of a perspective that. So in the last few slides I talked about scalar blocks, and the scalar blocks are kind of the things that have been used the most for numerical conformal bootstrap in the recent years, in the sense that most numerical conformal bootstrap studies were done with correlation functions of scalar operators. And now there have been some studies of correlation functions with spinning operators, with spinning external operators, but most of them didn't use these recursion relations in general, because it's a bit hard to compute this. The methods that were known for computing these matrices L and R were a bit kind of tedious, and some people, like, there was 1 or 2 papers where people did this for something like 4-point functions of vectors. But in general, this was not very popular. And what I'm going to talk about now is that we found a way to compute these matrices in closed form for all 4-point functions in 3 dimensions. So that's now situation is very different, that now we have closed form formulas, just like for scalar blocks, for all the components of the recursion relation, and so we can use them without having to work them out. And so let me discuss how we do this. So first of all, from the discussion that we had of this recursion relations, the things that we need to do to get to this point is that first of all, we need to understand when the pulse appears, and we need to understand what are the differential operators which come together with these blocks. And part of it has been covered in this paper by Pindonister, Zanya, and Yamazaki, but they mostly classified the scaling dimensions. They kind of done a review of mathematical literature on generalized Riemann modules, and they classified the values of scaling dimensions for which the poles appear. They did write some formulas for some examples of this differential operators D, but for more general results, we need to compute this D in general, and this is not in this paper, but the classification of quantum numbers was known. Now, after we have classified where the poles are, we found the differential operators. We need to apply those differential operators to the 3-point tensor structures to complete these matrices L and R. And additionally, after we've done that, we need to determine this function H infinity, which we know for scalar blocks, but we don't know in general. So we need to compute this function H infinity for general spinning blocks as well. And for all of this to work, we first of all also need to some way of describing 3-point structures for general spinning operators, for 3-point function and for 4-point function tensor structures. Now I'll only cover the part where about differential operators in this matrix L and R and the 3-point tensor structures. I'm not going to talk about H infinity and the 4-point tensor structures, just because it's not very interesting. The way it works is that if you choose a nice basis of 4-point tensor structures, you can just solve the Casimir differential equation to the leading order in closed form. Just if you choose a nice basis, the Casimir differential equation simplifies to the leading order in delta, and you can find these functions in closed form. But there is nothing special there. And so let me start with this. And I'm going to focus on, let me say that I'm going to focus on d equals 3, but the same methods can be applied in any number of dimensions. It's just that d equals 3 is simpler, so we did it there. Just the representation theory is simpler, and the Kravchuk coefficients and so on. So the first step is to classify these differential, conformal invariant differential operators when they appear and so on. So I showed you a picture before in case of scalar blocks, and it had 3 families of poles, and it turns out that more generally, in generic blocks, the table I showed you for scalar blocks had 3 families of poles, but these were not all the values for which this did not list all the values of delta for which the generalized Riemann modules stop being irreducible. It's just that for scale, it was only a subset, and the reason is that the null descendants that appear, they are not necessarily allowed to contribute to the 4-point functions of scalars. So let's say if you have some generalized Riemann module associated for which the highest weight state is some vector, then it sometimes has null vectors which are 2 forms. And in scalar conformal blocks, the 2 forms just do not appear. So this null descendants, even though they appear in the Riemann module, they don't contribute to the scalar block, and therefore scalar blocks have fewer poles than there could be in general. And if you get the general classification, then you actually get 4 families in 3 dimensions. In higher dimensions, you'll get even more families. And so this classification you can just pull out from this paper that I mentioned in the previous slide, but you can also get it in kind of a more hands-on way by finding kind of a clever way of detecting null descendants. And to do that, you can observe that you can create states in HO, not by just using the radial quantization, but you can go to a usual quantization by flat slices, which we discussed in the beginning of the talk, and you can create states there. And the way we create states in the usual quantum field theory is that we take local operators in Minkowski signature, Lorentz signature, and we integrate them over Minkowski space with some test functions and react in a vacuum. And this, provided that this is a smooth test function, this creates finite norm states, and this finite norm states are dense in the Hilbert space. And so if we just use one particular primary operator, this will be dense in our representations generated by primaries. And the nice feature about this is that when you take conditional conjugation in Lorentz signature, it doesn't do anything to X. And because of that, the norm of the states can be computed by transforming everything to Fourier space. And Fourier space, it just becomes the Fourier transform of Whiteman 2-point function, and you integrate it over a single momentum, and you have F and F conjugate evaluated at P. And so you have some integral over P, some function of P times these things. And having null states, having states which have zero norm, this can only happen when this matrix GAB of P has zero eigenvalues for some values of P. And so we can explicitly compute this GAB of P and see when it has 0 eigenvalues for some value of P. And this way you can detect null descendants without having to think about the generalized Riemann module and complicated representation theory. Something like this doesn't work in Virasoro case, because in Virasoro case, you are not going to generate all states in the Virasoro Riemann module by this kind of integrals, because you would need to add you would only generate the SL2C Riemann module, and there you want you would want to consider linear combination of this with other Virasoro descendants. But here, because the only descendants are generated by translation generators, this integral is enough. And a convenient way to look at this Fourier transform of Whiteman two-point function actually turns out to be to use the basis of spin indices for the operators, the local operators, where you transform the local operator to momentum space. Now you have this P, and you describe them by their spin projection onto the direction of P. So you have this index M, which goes from -j to j, and it describes the projection of spin onto direction P. So it kind of is, the base is dependent on P itself. And if we define the states OM of P by just acting with this Fourier transformed operator in this basis of indices on the vacuum state, then we can easily constrain the inner products of such states to be of the following form. And here we have a bunch of things which are fixed by symmetries, by obvious symmetries. So you have momentum conservation delta function. You have a power of momentum which is fixed by scaling invariance. And you have a Kronecker delta which fixes the spin projections to be the same just because of the Lorentz invariance. So if P is the same as Q, then in order for angular momentum to be conserved, M has to be the same as M prime. And the only thing that is unconstrained is some coefficient, overall coefficient, which can depend on the spin projection M. And well, when I say unconstrained, I say that it's unconstrained by dilatations, rotations, and translations. It is constrained by special conformal transformations. And you can, if you want, you can work out what is the constraint of special conformal transformations, and when it is, and it will become some recursion relation relating different dm, different values of m. But you can also just take the explicit formula for the two-point function that we know, and we can take the Fourier transform of it, and we'll find that dm is given by this expression, and we can check that it satisfies the recursion relation, which is imposed by the special conformal transformations. So the bottom line is that the states in our representation, which is described in this way, form essentially an orthogonal basis, and the norms of these orthogonal states are given by this function. And then you can just look at this function and see when it has zeros for some values of delta, it will have a zero for some values of m, and we'll find precisely this classification in this table that you can get from the representation theory of Riemann modules. But this is kind of a much more straightforward approach to it, without having to think about any kind of fancy mathematics. Okay, and in a similar way, it turns out that we can, using the same idea, we can actually get the explicit expressions for this differential operator as dm. Because if we ask how the differential operator as d can act on operators in this kind of representation, momentum space with this special choice of spin indices, you can see that it also should be very simple, because the momentum again should be conserved. So the operator, after acting with differential operator, we should get the same operator, the same momentum. But also the Lorentz symmetry, if you think about it, also fixes again the spin projection to be the same, and the dilatation symmetry fixes the power of p. And the only thing that's non-trivial is that there can be some m-dependent coefficient dm. And for the differential operator to be conformally invariant, so again here we took into account the translations, dilatations, and rotations. But for it to be conformally invariant, we need to take into account variance under special conformal transformations. And if you work it out, it leads to some recursion relation on these coefficients dm. And you can just then solve this recursion relation, so you can normalize these operators appropriately, and you'll find explicit formulas for different families. So for example, this is, I think, for the first family in this table. There are 4 families, and you have different operators within a single family are labeled by this k. And for a given k, you get an explicit formula for this coefficients dm. And you can just make a table of 4 simple formulas of this form, and this completely covers all the differential operators that you need to know. So I will now discuss the 3-point tensor structures and how we compute the action of these guys on the structures. But before that, are there any questions about what I've just covered? Okay. So if we go back to the discussion that we had, we can remember that the thing we need to compute is O2 and then this differential operator O acting on our 3-point tensor structures. And we need to expand it on some other basis. And before we can compute this action, we need to, before we can apply differential operator D to our tensor structures, we need to define this tensor structure. So we need to define what we mean by these expressions. And so this should be some conformally invariant 3-point tensor structures. And since they're conformally invariant, it suffices to specify them in any, to specify them completely. It's sufficient to specify them in any configuration of the 3 points. And it turns out that it's very convenient for our problem to specify it in kind of a bit wider class of configuration, not at one configuration, but in some restricted class. So particularly, we set O1 to be at the origin and O2 to be at spatial infinity. Well, at the point at infinity, we can work on Euclidean signature for this. And the operator O, we just put it at some position x that we don't specify. And the reason why we don't specify it is because we're going to be applying differential operators to it. So it's easier for us if we can keep it generic. And then what we need to write on the right-hand side is some function of x. But if you think about what kind of functions of x you can write, which would be reasonable from the point of view of dilatation symmetry and rotation symmetry, there isn't really much you can do. The things that you have are x mu essentially and the lengths of x. So you can put x to some power, and this power is fixed by dilatation symmetry. And then the only option that you have is you can put a bunch of x mu1, blah, 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 mu l up to some l. But this indices mu1, mu l, they are not the same indices that you have on the left-hand side, because on the left-hand side you have this indices a, b, c for the for the local operators, for the spin of the local operators. So what you need is you need to take some tensor, which is now x independent, which would take this mu1, mu l, and produce the indices a, b, c. And if you kind of ask what the transformation properties of this tensor are, is some tensor essentially which takes in a traceless symmetric spin L representation given by mu1, mu l, and it spits out 3 representations in this indices a, b, c, which are j1, j2, and j. And the way we can construct such tensors, especially in 3 dimensions, it's easy, is that we can take, maybe it's easier to think about this in other directions. You take representations A, B, C, which are J1, J2, and J spins, and you fuse them into some representation of spin L. And the way we would do this in kind of theory of angular momentum is simply that we would fuse spins J1 and J2 into some spin J12 using the 3J symbol or Kravchuk coefficient. And then we would fuse that additional with spin J using another Kravchuk coefficient, and we will get some spin L. That I will also denote J120 because it's, sorry, J120 because it's the kind of the total angular momentum of J1, J2, and O in some sense. And and the possible choices for this tensor for a fixed L of fixed J1 to O are just given by different choices of J1, 2 that you can put here in the intermediate step. And but since here we don't care about what L is, as long because it doesn't appear on the left-hand side, all possible choices for J1 to O are also acceptable for us. So to summarize this construction, we label the 3-point tensor structures by two numbers, J12 and J12O, where J12 is just everything which appears in the tensor product of J1 and J2, and J12O is everything that appears in the tensor product of J and J12. So according to this picture here. And then the 3-point tensor structures are defined so that in this configuration, O, infinity, and X, they're equal to these expressions, where the tensor T, this label alpha, is constructed by basically contracting the 3J symbols as in this diagram. And the advantage of this construction is that these expressions are very easy to apply Fourier transform to, because when you Fourier transform in X, since T is just a bunch of numbers which is X independent, we can factor it out. And what we need is we need to take Fourier transform of this expression. This expression has two properties. It has particular scaling with respect to dilatations, and it transforms in some traceless symmetric representation. And when we take Fourier transform, we should get an object which has the same transformation properties. But there is only one object which has the same transformation properties, and it's also P to the mu1, P to the mu blah blah blah, with some other power of P in the denominator. And the only thing that can happen is that we get some coefficient F, which is just some overall coefficient, which is just a bunch of gamma functions. You can compute it explicitly in some simple expression. So that's the way we define the tensor structures, and the reason why I define them is that it's easy to take their Fourier transform. Any questions about this?
Maybe I missed. Can you repeat again how to find it? How to find that alpha is a pair of numbers, and what is the meaning of these numbers?
Let me try to maybe formulate it a bit differently. So let's look at, we want to define this 3-point tensor structures, and this 3-point tensor structure should be conformally invariant functions. We want to write all possible conformally invariant functions with this transformation properties, with the transformation properties of these local operators that we can, and we'll label all possible functions by this label alpha, and that will be our basis. So to specify a conformally invariant function, it suffices to specify a conformally invariant 3-point function. It suffices to specify it in any configuration of 3 points. However, so let's for now, for the sake, temporarily imagine that X is some concrete point. So maybe like the first basis vector, E1. So if we specify a 3-point function at a concrete configuration of 3 points, there's going to be at most one conformally invariant 3-point function that has this value. But I'm saying at most one because it is possible to specify a a value such that there will be no conformal invariant 3-point function which will assume this value. And what you have to ensure is that the 3-point function that the value of 3-point function that you specify is invariant under the subgroup which stabilizes your configuration, right? Because if you fix 3 points, let's say, on a line, then there is going to be conformal transformations which rotate around this line, and this will be a group of transformations with d minus 1. And if you specify the value of 3-point function which is invariant under this group, then there's a unique way to define the value of this conformal of this 3-point function in any other configuration that's going to be conformally invariant. If the value of the 3-point function is not invariant under this SOD minus 1, then obviously there is no way to specify a conformal invariant 3-point function, because conformal invariant 3-point function should also be invariant under this subgroup. Now, so to specify, so from this argument, you can see that the space of 3-point structures is the same as the space of invariance of SOD minus 1 invariance in the tensor product of the two representations. So if you take row 1, tensor row 2, tensor row, which are the spin representations of O1, O2, and O, and you take invariance under SOD minus 1, then this is the same as the space of 3-point tensor structures. Now here I'm doing something slightly different. Instead of specifying the 3-point function in the single configuration, I'm specifying it for any x, but the position of O1 and O2 is still fixed. And in this case, what I need to make sure, analogous to this example, analogous to this construction, is that this expression that I specify is invariant now not under SOD minus 1, but under SOD and dilatations, because these are the transformations which kind of keep me inside the class of configurations that I allowed. And the claim is that any function of this form, that any function which is invariant under SOD and dilatations will have this form, but it will have this factor, because that's the only thing that you can write in terms of x. These indices mu with a bunch of indices, and it will be just contracted to some constant tensor. Now you can ask how many indices there is going to be, and the answer is that just you can choose a basis of structures such that in each element there's going to be some number of indices, and the number of indices that you have here is just going to be determined by whatever tensors you can come up. And so if you, in other words, you can argue that if you take all possible tensors, linearly independent tensors which have this form, so it carries this 3 indices ABC and also carries a bunch of trace symmetric indices, then from any such tensor you can construct a 3-point function that's going to be dilatations times SOD invariant by contracting with this factor, and in this way you'll cover all dilatations times SOD invariant functions of x, and by extension you will cover all conformal invariant 3-point functions. And after we've agreed on this, what I've done is I just enumerated all such tensors. And I'm saying that such tensors, they basically extract traceless symmetric representations from the tensor product of row 1, row 2, and row. And the correspondence with this formula is that only the trace symmetric tensors are the only representations which give you invariance which contain an invariant under SOD minus 1. So if you take tensor product of these guys, you expand it into reducible representations, only the traceless symmetric representations will contain invariance under SOD minus 1, and any traceless symmetric representation will contain a single invariant under SOD minus 1. And yeah, so what I want to do is I want to enumerate tensors which take row 1, row 2, and row 3 in row and project them into some trace symmetric representation. And in 3 dimensions, I can just do this by using 3J symbols.
No, this part is clear, yes. How to come from invariance to these numbers. No. Thank you.
Okay. All right. So the bottom line is that we can enumerate tensor structures by this pair of numbers here in this constraints. The meaning of this pair of numbers is that how we construct this tensor T using Kravchuk coefficients. And given this tensor T, we can construct the value of the 3-point function in this configuration. And then we can extend it to any other configuration by conformal symmetry. And the reason it's useful, this form, is that we can explicitly know how to apply Fourier transform to X, because it's very easy to take Fourier transform of this function and just multiplies it by some overall coefficient, essentially. And now with this, you can see essentially how we apply our differential operators D, because we determined our differential operators D in momentum space. And since we know how to get to momentum space, it's now easy to apply them. So in if you remember when I wrote this formula for that D taking an O with index M was dm times OM. This was for M, which is which describes the projection of spin onto the momentum. So everything is a function of momentum. So this M describes the projection of spin onto P. Here I'm just using some more abstract indices, and if I go to the indices which have the same meaning in momentum space, I have M1, M2, M, but the index for this trace symmetric representation is just going to be the spin projection 0, because you can see that here this trace symmetric representation, all the indices are contracted with P. So it doesn't have any spin projection on P. And so what I want to do now is I just want to multiply this tensor by dm, which is this, and I want to expand it in the linear combination of tensors without dm, but with some new j1, 2 prime and j1, 2, O prime. And if you now remember how we define these tensors, we define them in terms of product of 2 Kravchuk coefficients. So you have 2 Kravchuk coefficients here, multiplied by dm, and 2 Kravchuk coefficients here. And I mean, you can follow this through if you want, but the bottom line is that you can compute these coefficients now by essentially using orthogonality coefficient or orthogonality relations for Kravchuk coefficients. For example, here you can see that J1 and M1 and M2 only enter into this Kravchuk coefficient and not only into this Kravchuk coefficient. So orthogonality relations tell you actually that J1, 2 prime should be the same as J1, 2. And then, so you can cancel these two things. And then you just need to use another orthogonality relation to compute this L. So in the end, you get the formula of this form, where these coefficients L are given by just this coefficients dm, which we computed, multiplied by 2 Kravchuk coefficients. So this part is just coming from this left-hand side, and this thing just projects it into the particular structure, so it extracts just one coefficient. So you have the sum, and you can notice that the sum is very short in the sense that this projection M, it's a spin projection for representation J12, and so it's bounded, the sum is bounded by J12, the number of terms, and J12 is in turn bounded by J1 plus J2. So for example, for scalars, there's just one term in the sum. For, I don't know, for 4-point function of stress tensors, when J1 and J2 are equal to 2, they're at most like n terms in the sum, something like this. So it's the sum is finite for any choice of external spins. And then you just get these two coefficients f, which come from first taking Fourier transform of the position space 3-point function, and then taking the inverse space, the inverse Fourier transform. And so that's the code. That's the final formula, and these are just some explicit gamma functions that you don't want to write down. And as I said, in the case of scalar 4-point functions, you only restrict m equals 0, so there's just one single term in the sum, and it simplifies a lot to be just the single coefficient to 0. So that's kind of the sketch of the computation of this L and R, and the bottom line is that we can do this. We can also compute this as H infinity, as I said, and we get explicit expressions for these functions L and R. And so we have this, we've computed everything that we need for writing down these recursion relations for general blocks. You know, this matrix is L, R, no H infinity, and so we can go on and compute this power series expansion in terms of R for general conformal blocks. And we actually just, last week we published a paper which describes the software blocks 3D for doing this numerically. So you can, if you want, you can go to this website, you can download the code, compile it, and tell it, compute for me, please, the 3-dimensional conformal block with, you know, 4 spin 2 operators with this intermediate spin, with this scan dimensions, and hit enter and you'll do the calculation. So that's all I have to say. Thank you. And if there are any questions, I'm happy to answer.
I want to ask about the values of this delta i's. So are they all below this positivity bound, or something is above? So that most of them are kind of negative. So.
Yes. So all the poles of conformal blocks are below the unitarity bound, or exactly at the unitarity bound, because the unitarity bound just, so when delta is sufficiently large, all these matrices Qn are positive definite, and as you lower delta, at some point one of the matrices becomes, well, not one, but at some point some matrices become develop 0 eigenvalue. At that point you get the first null vector, but if you move any bit further, then they develop negative eigenvalues. So the unitarity bound is essentially for any spin, the unitarity bound is the position of the highest, of the largest pole in the conformal block, more or less. Sometimes it just happens that there is no pole at the unitarity bound. But you can derive the unitarity bound essentially by classifying these poles and finding the rightmost pole. Yes.
Thank you. And are there such situations, maybe like in 2D minimal models, where there are some operators corresponding to not reducible representations on the legs of a conformal block, and something like this going inside in such a way that effectively this possible pole is cancelled, and we get some finite expression.
Yes. So what can happen is that this matrix, well, in this case here it's a bit simpler than this, I think, because what can happen is that just so what you said can happen, but it can even happen easier than in easier way than this. It's just it can happen that this L matrix or R matrix is equal to 0, and it doesn't necessarily you don't have to have a special external representation for this. for example, one reason this often happens is that you take a 4-point function where you have, say, operators 1 and 2 are identical. And if operators 1 and 2 are identical, you have to impose permutation symmetry between them. And then you only need to use 3-point functions which are symmetric under this permutation symmetry. And depending on the parity of the intermediate spin, you can get different number of tensor structures which is symmetric. Often it happens that, let's say, there is a structure for even spin, but there is no structures for odd spin. And then if it happens that for your pole, it can happen that so when this happens, differential operators which change spin by odd amount have 0 residues, because in that case the null descendant simply doesn't appear because it would have odd spin. So the null descendant of even spin operator would have odd spin and it just doesn't appear in the 4-point function. So that's one situation when poles just vanish because of some kind of accident in some sense. But also it happens because sometimes it happens because you have very special relations between the scaling dimension of external operators, and that makes the poles vanish. Yes.
Thank you.
Okay.
So I may ask one more question.
Sure.
And what are the general situations? Maybe how to ask it. So what are the operators which usually appear in the physical theories? Are they all of generic dimensions, and only some of them like conserved charges corresponding to some special representations?
Yes, that's the case usually. So in 2D there is this huge story about physical operators being in short representations, right? But in higher dimensions, it doesn't happen. You can only have essentially the only operators which can be in special representations are conserved currents. And with conserved currents, you don't have many choices because in interesting theories, this is mostly just spin 1 currents and stress tensor. There is this result due to Moldasani and Zhabayedov that if you have higher spin conserved currents in higher dimensional conformal theories, then these theories are free. So interacting theories would only have spin 1 and spin 2 conserved currents, or spin 3.5 if it's supersymmetric. And everything else would be just some generic scaling dimensions. Of course, if you have supersymmetry, then you can have some short representations, and that's more interesting. But in bosonic theories, well, in non-supersymmetric theories, there is nothing else than like spin 1 current and stress tensor.
Thank you.
Thanks, Peter. If there are no more questions, then we just end the seminar. Thank you.
Thank you.
Thank you.
Thank you.
Thank you. Thank you.